Hello students, welcome to my YouTube channel Electrical Engineering. I hope all of you are having good time with your family and friends. In this lecture, I am going to demonstrate AC to DC converters, which are also called rectifiers. There are two types of rectifiers, half wave rectifier and full wave rectifier. And further, there are two other more types of half wave and full wave rectifiers, which are called uncontrolled and controlled rectifier. If the rectifying device in the rectifier circuit is a diode, then the rectifier will be called as uncontrolled rectifier, and in that case the firing angle is equal to 0. But in controlled rectifier, we have to use SCR, which is called silicon controlled rectifier, and with this circuit we can control this firing angle alpha by applying the pulse at the gate of this thyristor at any time. So if we are applying the gate pulse after this angle theta or after this angle alpha, which is called firing angle, the thyristor will turn on after this interval, and we can control this interval. So as a result, the rectifier output which we obtain at the end will be starting from this angle, and before this angle our output will be equal to 0. So in this figure, the dashed line is the input and the solid plot is that of the output. So when the thyristor gets turned on, the output will follow the input as shown in this figure. So this is the circuit diagram of a half wave rectifier. Similarly, we can also build a full wave rectifier which is composed of SCRs instead of thyristors. So first of all, we will discuss our results in the presence of the resistive load. And when we have resistive load, after specifying an angle of 45 degrees, such an output is obtained for the full wave controlled rectifier. Similarly, if we increase the firing angle to 135 degrees, then up to 135 degrees, our output will be equal to 0, and the rectifiers will be conducting only for this short interval, which is 45 degrees. So in this way, we can control the average value of the output, and in this case, the average value which is VDC is very high, and in this case the average value VDC is very low because the firing angle is very high and the conduction angle is very low. For the case of resistive load, uh, we have developed some mathematical expressions to calculate the mean value of the output voltage or DC value. So when the angle alpha is equal to 0, then VDC is equal to VD naught, and VD naught is the maximum DC voltage when the angle alpha is equal to 0. And we all know that for half wave rectifiers, VD naught is equal to V peak over pi, and full wave rectifier VD naught is equal to 2 V peak over pi. And this can also be represented by 2 over pi into square root 2 into VRMS. And for the controlled rectifier, when we have specified the value of alpha other than 0, in that case, our DC value will be a function of VD naught, and it will be 1 plus cos alpha divided by 2 into VD naught, and alpha is the firing angle. So if the firing angle is 0, VDC will become equal to VD naught, and if we have the value of firing angle other than 0, then the value of VDC will be reduced. Now we are going towards the practical implementation of these controlled rectifier circuits in Simulink. So this is the circuit diagram of full wave controlled rectifier in which we have used SCRs instead of the diodes. So these are SCRs, and they have the gate terminals. Uh, okay, so this is the gate terminal. You can zoom in and check. This is the gate terminal, and these are the pulses which we have to provide to trigger the thyristors. We have connected an ampere meter in series with the load, and we can plot our current waveform from here. We can also plot the voltage waveform over here. So these are the workspaces, and these are the settings of the workspace. So when we run this file, all of these variables will be stored into the MATLAB workspace, and they can easily be plotted after that. So these are the output voltages. We can calculate the DC value or the average value of the output by using this mean value block, and we can also visualize the switching waveforms or these pulses, and we can also visualize the input voltage together with the output voltage on top of each other. So we have to use a multiplexer block over here. So there is a very short and simple code which I have written over here, and this is the input AC voltage, this is the specified frequency, this is the amplitude of the pulse, this is the width of the pulse, this is the firing angle, and this is the time period of the pulse. This is the delay which we have given to specify the angle alpha. Okay, so one important thing over here is that if I double click on this pulse generator, you can see I have to specify the phase delay, and this phase delay is in seconds. This phase delay is not given in degrees. So in this code, first I am specifying the phase delay, which is the firing angle, as 90 degrees, but then I have to convert these degrees to seconds. Okay, so this is the expression which I have to use to convert degrees to seconds, and this is the specified load. First I will test my waveform for the resistive load, and then I will change my load to RL load by specifying a value for this imaginary part of ZL. Okay, so this is the command which is used to call this Simulink file, and this command will automatically run this Simulink file, and all of these variables which are terminated with the workspace will be embedded into the MATLAB workspace library over here. So when these variables are come to the workspace library, they can easily be plotted. So I am calculating the DC value for the resistive load, which is specified in this equation, and I am also calculating the mean value from this simulation, and at the end I will compare my results. So let's run this file. All of these variables are specified over here, and these variables are used directly in this simulation. So this is VAC and this is the frequency. Similarly, these pulse generators are also using these variables. And remember one thing, that this is the switch number 1, this is the switch number 4, this is the switch number 2, and this is the switch number 3. So switch number 1 and switch number 4, they will be triggered at the same time, and switch number 2 and switch number 3, they will be triggered at the same time. This is how a full wave bridge rectifier works. So I can specify one variable for triggering these two switches, and I can use one variable for triggering these two switches. So this is what I have done over here. So phase delay 1,4 and phase delay 2,3, they are used, and when you double click over here, then you can see P delay 1,4. So this same value is used in this block. Okay, so P delay 1,4. So now so similarly, P delay 2,3 is used for these two pulse generators. So let's run this simulation file and let's examine our output. So first case is the case when I have only the resistive load, because the imaginary part is made 0. So this is the final result, and the mean value that I have obtained is around 100, and this dashed curve is, say, showing the input, and this is my output. So the firing angle is assumed as 90 degrees, so I can see that after a duration of 90 degrees I am getting the output, and before this firing angle my output is equal to 0. And from that expression, the value of mean value of the output for the case of resistive load is 99.3127, and almost similar value is obtained by taking the average value of this output waveform. Now this slight difference between these two average values is attributed to the quantization error. If I increase my sampling time of the simulation, or if I reduce the sampling time, or if I increase the number of samples, in this simulation, then this value of the error will be reduced. So when I double click on this settings, you can see maximum step size is 10 raised to power minus 3. So this can be further reduced, and relative tolerance can also be further reduced. In that case, that error will be reduced. Okay, so now I am changing this load to RL load. Okay, so this is the reactance and this is the resistance. And when I go to the block diagram of the rectifier, this is the load. So real part of ZL is the resistance and imaginary part of ZL is the reactance. So this inductance is given in Henry, so I have to divide my reactance with 2 pi so that correct inductance value is available over here. So again, I can run this file. Okay, so in this case, the value of the output which I obtain is this. So after 90 degrees, I get this output waveform. But for further 90 degrees, I obtain the negative output. This is due to the freewheeling phenomena in RL load. Okay, so when I go to this lecture, you can see for the case of inductive load, my output stays positive, but it also stays for negative during the firing angle period. So this is the firing angle of 115 degrees. So for 15 degrees, I get the negative output. And if I increase the firing angle, my negative output will also increase. And for 90 degrees, you can see I obtain the output after 90 degrees. But for other 90 degrees, I get the negative output. So this is the case for the RL load. So this is the diagram of the RL load, and these are the waveforms of the input, V out, and the waveform of the current. So such a waveform is obtained from the circuit, and now you can see the value, mean value is almost equal to 0. Ideally, it should be equal to 0, but it is equal to 3. And again, this error can be reduced by increasing my samples and by decreasing my relative tolerance. So that is all for today's lecture. I hope you all have understood the implementation of half wave or full wave rectifier in Simulink. Similar way, we can also design a half wave rectifier circuit, and I can run this file. And when I double click on the scope and when I click on auto scale, you can see this is the duration at which I apply the pulse. And when the thyristor switch gets the pulse, it is triggered on and it is producing the output which is following the input. And again, for the negative cycle, there is no output because this is half wave rectifier. And for the other next positive cycle, again after the angle of firing angle, which is specified as 50 degrees, I get the output again. So we can see such a waveform for full wave rectifier circuit as well. And that is all for today. For watching similar videos, please stay tuned to my YouTube channel. Until the next video, it's goodbye.